problem from everyone. So welcome everyone to today's seminar. Today we have Leandro Beraldo Silva, who is a researcher at the National Observatory in Leandro. He did his undergrad, master's, and PhD at USP with a sandwich period in Paris at the IAP. He then held postdoc positions at USP, UCLan in the UK, the University of Michigan, and the University of Arizona, the Stewart Observatory. He's recently been hired at ONE, and he's also co-chair of the Milky Way working group of the DESI collaboration. Thank you so much for accepting our invitation. Leandro, you may start when you're ready.
Thanks, Anna. Thank you very much. So, okay, let me start sharing my screen. And actually, I don't know what's the tradition of the seminars. If people normally ask questions in the presentation or only at the end, but for me, it's only at the end. Okay. Yeah, just to make clear for me, it's fine. Yeah. Okay, so let me put this in presentation mode. Yeah, and just to let you know, in any case, I'll be seeing my slides and I probably won't be seeing the Zoom. But anyway, okay, so thanks everyone. Thanks for the opportunity to talk about my work. So this is a method that I have been working in the last year or so. It's the idea is to constrain the Milky Way potential based on this minimum entropy principle that I'll explain next. Okay, so just a brief summary of what I'm talking about today. So I'll first talk about this method. I'll go right away to the method, and then I'll explain kind of the physical base for it, why it works, because it can be a little bit unexpected that it works. And then I'll say a few words about the DESI-Milky Way survey and the DR1 that was just released. Okay, so, okay, this is based on this paper that is still on the archive, not published yet, but I hope it's close to that. Okay, so we all know that the Milky Way has several different components. We have a thin disk, a thick disk, a bulge, and we could list it, even others here. But we are mostly interested in the dark matter halo and also in the stellar halo. So I'm putting here in gray what could be something like the dark matter halo, and some stars also the stellar halo. Okay, and for the dark matter halo, we actually don't know really its shape, if it's spherical or flattened or anything like that, right? And the main idea here is try to constrain the shape of the dark matter halo. This can have implications in cosmology, in particle physics, because depending on the type of particle that you assume for the dark matter, you typically form halos of different forms. So that's the main motivation here. Okay, the problem is that we know that for the Milky Way and for galaxies in general, most of the mass is in this dark matter, but this is unseen, which means that it's really hard to constrain this mass distribution and the shape of this mass distribution. So in order to do that, essentially we have to use stars. Then we need to translate positions and velocities and the kinematics of stars into constraints for this dark matter halo potential. Okay. So a fundamental assumption here is that the stellar halo is in equilibrium. So it makes a system that is in dynamical equilibrium. We know that it's not strictly true, depending on the region where you go. If you go far enough, you have the perturbation from the LMC, for example. But for some restricted range, it's still a reasonable assumption. So the nice thing is that if this stellar halo is in equilibrium, you can use Jean's theorem. Jean's theorem tells you that the distribution function f, which in principle is a function of positions and velocities of these stars. So in principle, it's a function that lives in a 6D space. But from Jean's theorem, if the system is in equilibrium, you can assume this df is actually only a function of the integrals of motion, which can be 3, 2, 1, depending on the symmetries of your problem. And so this is a drastic dimension reduction, very, very important for this problem. Okay, so I'll just mention here one technique that people has used in the past to do this. That's this DF fitting, the distribution function fitting. The idea here is, again, you assume the stellar halo is in equilibrium. You use Jean's theorem, but now you assume some functional form for the DF as a function of the integrals of motion, and also for the potential that you want to constrain, right? You assume some functional form with some parameters, and you fit these parameters for both functions, okay? So, and then you define the likelihood of your sample is this, is the product of your DF evaluated at, for every point in your sample. And then you have your log likelihood, it's just this expression here, it's the sum of log F, right? Evaluated at every point in your sample. So, and the thing is that the potential that you want to constrain, it enters the fit through the integrals of motion, because the integrals depend on the, for a fixed sample, for fixed positions and velocities, the value of the integrals depend on the potential that you are probing, be it the energy. The angular momentum doesn't depend, but the actions also depend. And I'll mention here that the method that I'm mostly focusing here is based on actions. So you assume the DF is a function of these action variables. That's also the method that I'll explore here. But in principle, the thing can use any integrals of motion that the symmetry of your problem allows, okay? Okay, so some problems with this approach. We actually don't know what's the distribution function, what's this functional form for the DF, and we cannot, I won't say you cannot, but it's really hard to constrain this, okay? And then what people normally do is just propose a very generic expression for this F, which depends on several parameters. And then you also need to fit for these parameters. But if you are only interested in the potential, you marginalize over these parameters for the DF and you constrain your potential, okay? That's the kind of thing we are trying to avoid here, okay? This minimal entropy method actually tries to generalize this maximum likelihood method in such a way that you don't need to assume a functional form for your DF, okay? Okay, so let's go to this minimal entropy method. So the idea here is that for any DF, for any distribution function, even out of the scope of galactic dynamics or anything like that, for any probability distribution function, F, you can define the entropy in this way. It's just a definition. It's the integral of F log F over your space. And the nice thing is that you can actually estimate this entropy with a Monte Carlo principle, essentially summing over the points of your sample, right? So if you think about it, this is the average value of log F, and this is exactly the average value of log F. You sum over particles here, okay? Of course, the hard thing here is how to estimate the DF at the location of each point. And there are different methods that you can use. But here I'm going to talk about the nearest neighbor method, which has been shown to be very good, to have very good mathematical properties. The main idea here is essentially 1 over the distance in phase space, the power 6. So this is essentially the volume of a small sphere around each point, okay? So just to illustrate, suppose you have a sample like this, some points, and then you take this point here, identify the neighbor, you say, okay, this is the nearest neighbor. I define this hyper sphere in 6D, let's say, with this radius here, and then the estimate of the density in this point is the number of points in this sphere, 1 over the divided by the volume, is d to the power 6. There are some normalization factors here, but I'm not entering details here. Okay, so, and then remember, I'm connecting here now this expression for the entropy estimate with the expression for the log likelihood that we had before. If you compare these two expressions here, essentially this motivates you to define some kind of log likelihood that I'm calling log lambda. This is essentially minus n times s, okay? This is not really a log likelihood for some technical reasons, but the nice thing is that this function here, log lambda, it has a maximum at the same location of your log likelihood, and it has the same value of the log likelihood at that point. So you can translate that, you can still maximize this function, which means you are minimizing these entropy estimates here. That's why we have this minimal entropy principle, essentially. So the main idea here is maximize your likelihood. It's essentially the same thing as minimizing your entropy, with the advantage that you don't need to assume any functional form for your DF. That's what we are doing here. Okay, so let me show some expressions and some results regarding this entropy estimate. So again, we define the entropy like this, and we use Jean's theorem again. If the system is in equilibrium, you can assume the df is a function of integrals of motion only. So for example, for spherically symmetric and isotropic systems, you can assume the df is a function of energy, and then that same entropy reduces to this expression here. So it's a little bit complicated, but I'll just show some expressions. So in the case you have your df also depends on angular momentum, for example, you have something like this. And in the case you assume the arguments of the df are action variables, you have something like this, the entropy reduced to this expression. Okay, where this big F here is the real PDF of the integrals of motion. This is always your df times this density of states, something like that. All of these are only functions of integrals of motion. Okay, so now I'll show you some tests of these entropy estimates, how they look like, how good they are. And for this, I'll use this isochron model, which is a really good model in galactic dynamics because it has analytical expressions for everything. So we know the true answer and we can compare with these estimates, okay? We have analytical expressions for the action variables, for the distribution function, and for the density of states too, okay? Okay, so just show, so in this case, because you know for a self-consistent sample of the isochron potential, you know the true answer, and the true entropy is easy to calculate, is just a 1D numerical integral. I calculate this is shown here by this thick gray line here. So this is the true value. Now I generate a sample, a self-consistent sample of this potential, and then I estimate the entropy based on this sample, okay, with these techniques that I was talking about. So this, and here I'm showing this as a function of time because I generate this initial sample, and then I integrate orbits for all these particles at once, okay? I'm integrating orbits for all of them, and then I estimate the entropy at different times, okay? So this is just to show that this entropy is conserved, as it should be, because you have this self-consistent sample. So this sample is stationary, is in dynamical equilibrium, the entropy should be conserved. You have, of course, some fluctuations, and this is for 10 to the 4 points, when I have 10,000 points. And this is what I get when I increase the number of points up to 10 to the 8, in this case. You can see that, okay, it's a nice thing that the entropy is conserved, and it's clear that we have a bias here, okay? This is well understood. We are in 6D. It's really, really hard to populate a 6D volume and to get these estimates with, let's say, zero bias, right? But we can see that when we increase the number of points, the bias is reduced, okay? But again, we are estimating things in 6D here. So this is what happens now when we estimate the entropy. Note, I forgot to mention here. So here I'm estimating the entropy in 6D. I'm not really assuming equilibrium. I'm just estimating the entropy and seeing what I get. So for these dashed lines here, what I see is that, okay, I assume this system is in equilibrium, and then I assume the df is only a function of the actions, the 3 actions. So I'm reducing the phase space here from 6D to 3D. Then I estimate the entropy in these 3 dimensions, okay? And so this is what we get. Because of this dimensional reduction, you see that this bias is much smaller. Yeah, I'm much closer to the true answer, okay? And this is just showing the relative error, let's say, the relative bias for different numbers of points in different spaces. So this is in 6D. Again, you can see that the bias is relatively large. And all of these points here are for these entropy estimates in different spaces of integrals of motion. So the triangles are for action space, and the crosses, for example, are when I assume the df is a function of energy and angular momentum, so in 2D, and the points are for when I assume the df is a function of energy only, so in 1D. You can see that when you reduce the dimension of your space, your estimates get better and better. Okay? But they are pretty good already in 3D when you use only actions, as you can see here. Okay, now I do a different exercise here. I used exactly the same initial sample. It's the same initial set of points, right, that are self-consistent. In this isochron potential, I forgot to mention here, I had mass equal to 1 and scale length equal to 1, let's say. But now I use the same sample and put this sample in the isochron potential with 3 times the mass, a higher mass, okay? So now this sample is not in equilibrium in this different potential. The sample will phase mix, okay, in this new potential. So you expect some kind of re-equilibration of the sample. And this is, oh, by the way, so I forgot to mention this thick gray line here is also the true answer in this new potential. That's where you would expect your entropy to converge to. Again, we can see the bias here, and we do see this entropy increase over time, okay, when you integrate these orbits. But again, when you use actions as arguments for your DF, you are much closer to the true answer. Okay, that's what this is showing. And this is just to show that you had this bias in the initial estimate. You also have the bias in the final estimate. But when you calculate just entropy variations, delta S, you actually get very close to the true variation. Like, even in 6D, you cancel the bias essentially. Okay, so there is one important point here is that these systems are purely collisionless, right? So you are just integrating orbits in a fixed potential. So there is no self-interaction, collision, or relaxation, anything like that. And it's traditionally assumed that if the system is collisionless, it is necessarily described by the Vlasov equation, which is df dt equal to 0. Essentially, the df is conserved somehow. The problem is that this implies that the entropy should be conserved too. Okay, so we have a problem here because we see this entropy increase, and the real big problem is that for the Jeans theorem to be satisfied, for this final sample to be described by a df that is a function of integrals of motion only, you have to increase the entropy. Okay, so you see there is a big problem here between these two cornerstones of galactic dynamics. On one hand, you have the Vlasov equation. On the other hand, you have the Jeans theorem. So I will claim here that this description by the Vlasov equation is actually problematic for collisionless gravitational systems, and I'll explain that better later. Okay. Okay, so this is now just to illustrate that we really have the correct potential. If we try to recover now the potential based on this idea, let me get a step back here. So the idea here is then, okay, if you have your sample that you assume is in equilibrium in the correct potential, the idea is that if you put this sample in any other potential, the sample will phase mix, and that will increase the entropy of the sample. So, but now if you have a fixed sample, the idea is to recover the correct potential by minimizing the entropy then, because you know that any wrong potential would increase this entropy. Okay, so this is just illustrating this. I have generate the initial sample of the isochron potential. Let's see, the magenta point here is showing the correct values of the parameters. I have the scale, the mass, and scale length. And then for this sample, I estimate the entropy in several different potentials here, right, in a grid. And then I calculate the entropy in each one of these potentials and check where's the minimum of this entropy. And the minimum is in this white cross here. You can see that it's really close to the true potential, okay? So this is just to show when I take k equal to 1, it's the first neighbor. This when I take k equal to 10 is the 10th neighbor. You can choose which neighbor you take. It's a well-known fact that when you take larger neighbors, this smooths out your surface, your estimates. So this is what we are seeing here. But the main point is that the minimum of this entropy is really at the correct potential, very close to it. Okay, that's the idea behind this method here. Okay, so this was not a fit yet. So now we are going to make a fit. Once more, so the first step here is to find the best fit potential. And again, I generate a sample of this that is in equilibrium in the isochron potential. And now I forgot about the true answer and just estimate the entropy of this sample in different potentials and minimize this quantity, okay? Okay, so this is what I get. So this is a true fit. So the red point here is the fit that I get for this single data set. And then I can generate different data sets via bootstraps just to check. This is kind of a frequentist way of exploring your log likelihood surface, more or less. It's not exactly that, but it's more or less that. So each point here is a fit obtained with a different data set that was generated by bootstraps. And we can see that all of them, orbit around the best fit, the true values here, as we can see. So this is showing that this method is working for to recover the true potential, at least in this simple case. Okay, but once you find the best fit model, you also want to explore the posterior of these parameters, okay? Then you can evaluate how correlated are these parameters and the uncertainties on them. There's a problem here because we are not using likelihoods here, as I mentioned. So we don't have an analytical expression for the DF, we don't have a log likelihood. And all these, for example, if you use EMC, for example, to explore your posterior, I'm sure some of you already use that. All that machinery assumes you have a likelihood, but we don't have that here. So we have to use a different machinery. And so I'll explain that in a second, but just to explain the main idea here. So once you find the best fit potential, you calculate actions in this best fit potential, and you assume the DF described in this sample is this F0, as I'm calling here. And then, because of the reasons I was explaining, you need to use this approximate Bayesian computation. Sometimes people call this likelihood-free estimates or something. So again, you can sample your posterior, characterize your posterior probability without assuming likelihood. That's what we are doing here. For that, I use this software here by ABC. It's called, and then the essential idea is that for each potential, for each model that you are probing, you need to generate a new data set. So this is sometimes also called simulation-based inference, because you need to simulate, generate different data sets for each model that you are testing. And then each trial model here is characterized by a DFF, and then you have to define a distance metric, let's say, between your observational data or your best fit model, this F0 in my case, and each trial potential. So the trial potential is F. And then for this distance metric, I'm using this quantity here that is called the Kullback-Leibler divergence. And the nice thing is that this can also be estimated, even when you don't know the analytic expressions for the distribution functions. This can be estimated with Monte Carlo once you just have samples at hand. Okay. Okay, and then the thing is, okay, you accept some model if this distance here is smaller than some distance threshold, and this distance threshold actually evolves iteratively. So this is a little bit technical, but and then this is as I already mentioned, this is an iterative process. Okay, it's a little bit technical, but just to illustrate how this works. So essentially, you start sampling from some prior that you choose. In my case, I have a flat prior, just blank here because these are potentials where we would have unbound stars. I'm not fitting for them. But then the algorithm iterates here until you have a sense of convergence. That's what we're seeing here. The posterior converges to this, and the magenta point is actually the correct potential. So you can see this thing is really working. So these are the final contours that we get to explore the posterior parameters for this. As I mentioned, each model has to be followed by a different data set. You need to generate new data sets. So here I'm showing two different techniques to generate these data sets, either by bootstraps or by sampling from some assumed Gaussian error distribution for each of the coordinates, with here relative errors of 10%. Okay. So essentially, you can see that this is working. It's recovering reasonably well the true parameters of the potential. Okay, so the next step, of course, is to go beyond spherical symmetry. This potential that I was showing you is spherically symmetrical. The next step is to go to something that is not. So I tested now a dark matter halo that is flattened. So I fixed this dark matter halo with a flattened parameter 0.7. And I'm fitting a model here that actually has 4 parameters. So this rho 0 is the normalization, the density normalization. Q is this flattening parameter. Gamma is the inner slope of this dark matter halo. It would be -1, for example, for an NFW profile. And RS is the scale length. So 4 parameters. And again, I have this potential, and I generate a sample that is in equilibrium in this potential. And then I forget about the potential, just get the sample, estimate the entropy in different trial potentials, and get the minimal one, and then explore the posteriors, as I mentioned before. Okay, so this is what I get when I do this resampling, as I mentioned, assuming Gaussian error distributions of 10% for each coordinate. Uh, well, the fit is a little bit complex. We have all these 4 parameters here, but I'd like to focus mostly on this Q parameter here. Again, this is the flattening parameter. So this is what allows us to disentangle if this dark matter halo is spherical, in which case you would have Q equal to 1, or flatten, as in this case here. But in essence, you see that we can go beyond the spherical symmetry and we can still recover the true parameters with very good precision. So this is just to compare what we get when we have 20% error, relative errors on each of the coordinates of our sample, which is a little bit conservative, I would say, pessimistic. We can do better than that in the Milky Way nowadays, but we can still recover all these parameters, and in particular the Q parameter, this flattening parameter. Okay. Okay, so this is the main thing about the method. That's what we have for now. And now I'll say a few words about the physical base of the method, and again ask this question: why does this method work? Because remember, we are talking about collisionless systems here. Okay, so we are just integrating many orbits. Well, actually, let me go back here. In the method itself for fitting the potential, we don't need to integrate orbits. Okay, it's just a static sample that we have. But in that problem that I was showing before, when I was integrating orbits, this is a purely collisionless system. Okay, there's no two-body relaxation, nothing like that. And it's traditionally assumed that whenever you have a collisionless system, this is well described by the evolution of the system, is described by the Vlasov equation, the FBT equal to 0. Sometimes people call this collisionless Boltzmann equation. I find this name particularly confusing. I can talk more about that later. But anyway, but the problem is that if this equation is valid, the entropy should be conserved during the evolution of this sample. Okay, so what is happening here? What's the problem here? Okay, so let's talk about some possible reasons for this entropy increase that we observed, and that is explored in this minimal entropy method. Okay. Okay, so the most immediate thing is, okay, each orbit for each star, let's say, is time reversible. Like Newton's equations are time reversible. Okay, so why would we have time irreversibility in this problem? Okay, that's the most immediate question that you can ask yourself. So the answer to this is conceptual, but it's easy to understand. So there is a fundamental difference here between the microscopic description of the system and this macroscopic description. By macroscopic, I mean when you consider each point or each star individually. And so it's true that the equations of motion are time reversible, but here we are not talking about one star or one particle. We are talking about the evolution of a system as a whole. And so that's in this macroscopic sense, that's where the irreversibility appears. And so some author says that this was already well solved even in Boltzmann's time, so there's no reason for confusion about that. Okay, so the other point would be, okay, you see this entropy increase, this irreversibility because of some truncation errors. Computer calculations are not perfect, so that's the reason. Or the other possible reason would be, okay, you are coarse graining. So the whole idea of coarse graining is that this Vlasov equation predicts the existence, the development of very fine scale structures in your phase space. But whenever you're making measurements, you lose information because you make averages on phase space. And this entropy increase would result only from this information loss, let's say. In this sense, it's kind of artificial, this entropy increase, okay? I hope to convince you that it's not any of these reasons. The reason for it's not due to coarse graining, this entropy increase. Okay, so some ingredients for this irreversibility that people might think about is chaotic mixing. Like, okay, you need to have chaotic motion to observe an entropy increase in your system, or you would need to have a time varying potential. For example, that's what Lindenbell proposed in the 60s for the violent relaxation process. The idea that when the system is collapsing, the potential is time changing, and then the particles are exchanging energies because of this time changing potential. and that's what generates this relaxation, this irreversibility. Or you could say that, okay, it's just because you have a large number of particles and phase mixing, that's enough to produce this entropy increase and this irreversibility. So that's the point I will advocate here, that that's exactly what is going on. Okay, so here I'll mention some like old results that I have regarding these entropy estimates and showing these ingredients for irreversibility. In this case, I did a very similar thing. I have a fixed external potential. I set some initial condition of some particles there and integrate orbits for these particles. And then I estimate the entropy in the same way as I mentioned before. Okay, so I did that in integrable and also in non-integrable potentials. And then I check the influence of the end dependence of your sample and also a connection with the Nyquist-Shannon theorem that I'll explain in a moment, which is very illustrative of what's going on here. Okay, so this is similar to a plot that I showed to you before, except that in this case, we have the Plummer potential, just a different potential, and I have the entropy evolution as a function of time for two different samples. One sample is when I start with a generic initial condition that is not in equilibrium with this potential, like nothing to do with that. Again, integrate orbits, estimate the entropy, and it evolves like this again. It goes to a stationary state at the end, which should be equivalent to the compatible with the Jeans theorem. And on the other hand, when I start with a sample that is self-consistent, so it's in equilibrium, this potential, the entropy is perfectly conserved. So this is just to emphasize that if this entropy increase that we observe here, if that was due to any truncation error or anything like that, we would also observe this entropy increase in this case, and we don't. So this is showing that this entropy increase is not due to that. The other important thing to emphasize here is that these are spherical potentials. Spherical potentials are integrable, which means that there is no chaotic motion here. Every orbit is regular. So we also see that for this entropy increase, chaos is not important, okay? At least it's not the most important ingredient. Okay, now I will say a few words about this end dependence and the role of chaos for this entropy increase. So for this, I used a different potential here. It's not a spherical potential anymore. It's a triaxial potential, which can have different inner slopes. In the case gamma equal to 0, we have this perfect ellipsoid potential, which despite being triaxial is still integrable. So every orbit here is regular. There's no chaos here, okay? And I also investigated this another potential with a weak cusp, which is non-integrable and has chaotic motion, and another one, strong cusp, with even more chaotic orbits, okay? So, and I did exactly the same thing, start with a generic initial condition, integrate orbits for them, and estimate the entropy in different times. Note that here we have log scale, and this is for the perfect ellipsoid, integrable potential, and we see exactly the same thing, this very quick entropy increase. And different colors here are for samples of different sizes. And you can see that when we increase the sample size, we delay the entropy increase, okay? So, and so this is showing, in fact, in the limit of infinite number of points, you would have entropy conservation here, okay? And in fact, the Vlasov equation is based on this assumption that you have an infinite number of points, okay? So in the limit n equals to infinite, you would have entropy conservation and would be compatible with Vlasov equation. But here we can see the extrapolation to the realistic number of stars in our galaxy. It's 10 to the 11. So you can see that even in this case, this entropy increase very quick after a few crossing times. And galaxies are hundreds or even 1,000 crossing times old, okay? So this entropy increase is really relevant for the evolution of a galaxy. That's what this is showing. This happens even in integrable potentials. And this is what we see in this weak cusp potential or strong cusp potential. And we see a similar thing, but now we can investigate what's the time scale for this entropy increase more precisely. So I define this time scale as the time where this entropy increase, this entropy crosses half of this asymptotic value here. And then I'll show at which time each one of these curves cross this line here, okay? So this is what we get here. So this is the, let's say, this collisionless relaxation time. as a function of n. And so we see this for the perfect ellipsoid, for different symbols are for different potentials. And the main thing here is that this is for integrable potentials, or in the presence of chaotic motion, or even more chaotic motion. Okay. So one important thing here is that so chaos is not really important for producing this entropy increase. It's not the main ingredient, but it seems to accelerate the entropy increase. You see that when you have more chaotic orbits, this entropy increase is anticipated. Okay. But then the question is, you can see that this time scale is approximately n to the power 1/6, as you can see here. Okay. And then it's intriguing, right? Why exactly this n dependence 1/6? Okay, this brings us to the connection with this Nyquist-Shannon theorem. Let me explain what is this in the most simple terms as I can. So assume you have a function here as a function of just one variable x, and it has this parameter k, which is essentially the frequency of oscillation of this function here. Okay, and we are interested now in, okay, you assume this function in the continuum, and you want to sample this function, generate points based on this distribution function, let's say. Okay, and we are going to use 10,000 points, and in 2D, you assume that in x and in y, let's say, you have the same function here. Okay, so this is what you get for a fixed value of this parameter k. It's the frequency, right, of your function. You can see that with this number of points, you can see the oscillations of the function. You can see the fine scale structures of your function. Okay, so when you increase your function and you are still sampling with the same number of points, you increase to 16. You can still see this. Okay, but and here, even here, you can still see. But when your function oscillates too wildly, right, too fast, you have a large frequency, you cannot reproduce the oscillations of this function with this fixed number of points anymore. Okay, you would need many more points to reproduce that. Okay, that's exactly the content of the Nyquist-Shannon theorem. So if you assume a function in d dimensions, okay, and then you want to and you assume this function has a largest frequency k, and you want to sample this function. This requires this puts you a minimal number of points to reproduce all the features of this function. Is this frequency k to the power d, and this is the dimension of your space here. Okay, but very important here. This is a very important point of the talk. So this is not actually the situation we have when we are investigating nature, let's say, because we are not given an analytical function, a smooth function. We are always given a finite sample. Okay, you have a number of points, number of stars in the sky, let's say. Okay, and then if you assume a sample of size n, that puts some constraints on the possible functions that you can attribute to that sample. Okay, and you cannot attribute a function that oscillates too wildly to that sample. I mean, you can do that, but you are introducing information that is not in the sample. Okay, that's the main idea. So that's the inversion of this relation here, and that's again the other side of the Nyquist-Shannon theorem. So this is exactly what explains that time dependence that we saw before. It's n to the power 1/6 approximately, because you are in a phase space of dimension 6. That's exactly what we see there. So just to illustrate this, so this is not based on time, this thing that I was talking about, but that's exactly what time does when you have a sample evolving in space. It can be stars in the sky. Okay, so you have a fixed number of stars, 10 to the 4, let's say, and your phase space starts developing these fine structures. It starts developing, but then it can only hit a limit, and it goes to a uniform distribution after that. Okay, so there is no need for coarse graining here. The fact is that you have a finite number of points, and that limits the fine scale structures that your system can develop. That's the main thing here. Okay, so this is kind of okay. Just to go back to this point. So collisionless systems are traditionally assumed to be described by this equation. The entropy should be conserved in this case. The problem is Vlasov assumes you have an infinite number of points, which we don't, right? So the number of stars in a galaxy is finite, is 10 to the 11, let's say. There's nothing we can do about that, okay? And then because of that, this theorem, it forbids the development of structures that are too fine in our phase space, okay? So there's no coarse grain here. There's no need for that. the system relaxes spontaneously. There is no need for this external intervention, let's say. Okay. And then, of course, this assumption breaks early, and also Vlasov equation breaks early. Okay. Okay. So after all this theory, I hope you survived. But now I'll say a few words about the DESI survey, and I think I'm close to time here. Okay. So DESI is a multiplex spectroscopic facility. It's installed in a 4-meter telescope at the Kitt Peak National Observatory in Arizona. It has 5,000 optic fibers that are robotically operated. So this is a very efficient way of taking many spectra at the same time. Of course, you set your targets before for the night and so on. You choose your targets, and for each exposure, the robots point to your objects, take spectra of them. Then you move your telescopes, and the robots assume the correct position for the new objects again. Okay. Okay, so this is just a picture of the Kitt Peak, and the Mile telescope is here, the 4-meter telescope. I think these slides here are actually from Tucson, which is a nearby city. So this is a picture of the telescope inside the dome. And here is the focal plane, and this is exactly where all these optical fibers are located, and these robots. And so this is just a picture showing some of these robots, some of these fibers that are robotically operated. And this is the back part of this petal here, and where we see the fibers going out here, and from here they go to these spectrographs. Okay. Okay, so the first data release of DESI was just released. It provides spectra for more than 18 million objects. So from these, we have approximately 13 million galaxies. That's the main the main point of the survey is in principle a cosmological survey. Also 1.6 million quasars, but it also has spectra for 4 million stars, because DESI also has a Milky Way survey. Okay. Okay, so these are just a few pictures. This is from the DR1 paper. So these are actually showing as a function of redshift this cosmological survey. The locations of each point here is a galaxy or quasar, things like that. And you can see the footprint of the survey here. These are regions that will still be completed in the next data releases. And this is for the Milky Way survey. We can see the spatial distribution here of stars that for which we already have spectra. And this is showing X, let's say in the plane of the galaxy, and this is Z, the distance above it and below the plane of the galaxy, the Milky Way. And this is color-coded by metallicity, and we can see nice metallicity gradients here, and so on. Okay, so the resolution is a low resolution spectra. So this is 2,500 to 5,000 resolution. So, but the really nice thing here is about the number of stars. It's really huge. But even with this low resolution, we have pretty good precision on the line of sight velocities of order 1 kilometer per second or 5 or 10 kilometers per second. That depends on the metallicity and also on the magnitude. The precision on metallicity that we have for the estimates is on average 0.1 DEX. Of course, for some, for many stars, is even better than that. And as I already said, we have 4 million stars just in the first data release. So this is just to mention, because DESI works with these, it has different surveys actually, and each survey has different programs. So I'll focus here on the main survey, and we have these different programs here, backup, bright, and dark. This bright program is actually the program that is shared with the Bright Galaxy survey that is in the cosmological survey. And this is it's really where the meat of the survey is. You can check the number of stars here with spectra. The backup program is observed in really poor conditions. So it's really when you have your fibers there that you are not using for anything else, and you just take spectra for stars. And even in this case, you can still take a pretty good spectra for many stars. Okay, and this is just to show how the DESI-Milky Way survey compares with different surveys as a function of magnitudes here. And this is number of stars per beam. We can see the different programs of DESI here. We see DESI Bright here and DESI Dark and the backup program. And how this compares with Gaia RVS. You can see that we can go much fainter here, and also how this compares with LAMOST, which go similarly fainter, but we have many more stars in this, for many more faint stars, as you can see here. Okay, so I'll just say a few words, a summary of the talk. So I talked a lot about this minimal entropy method to constrain galactic potentials. And for the Milky Way in particular, I still don't have the results for the Milky Way, but the whole idea here is to constrain the Milky Way. And why this method works is because real systems are finite n, and we explore this fact. That's why this phase mixing process produce this entropy increase, and how systems really relax these collisionless systems. Just what I just said, that DESI just released the first data release. It has 4 million stars. The Milky Way mostly are in the halo, but we also have many stars in the thick disk and even in the thin disk. Okay, so next steps here, I essentially use DESI data in complement with Gaia, and to constrain the Milky Way potential, applying this method that I talked to. Okay, and that's it. Thank you.
Questions from the Google Doc, but if you would like to ask, please feel free. If not, I'll have to ask. So there's one question that asks, could the galaxy gaseous component affect your results?
Well, you can consider like the gas component for the contribution of the gas to the potential. Yes, and you can even like try put that to model this, right? You assume some analytical form for the contribution of the gas to the potential, and then you can fit for that. It's a little bit harder to constrain, but it's possible to do that. Yeah. I mean, I hope that was the question.
Okay, please go.
Well, in principle, it is also only used for the Milky Way, your work. It is a disk galaxy, and in principle, the disk respond to maximum entropy system. You can constrain your potential with the disk of the galaxy, not only with the star of the bulb. How do you use these two systems?
Yeah. So not sure if I understood the question, but let's see. So the thing is, the idea here is not to use stars in the disk as tracers, because remember I mentioned a fundamental assumption here is that your sample, your system is in dynamical equilibrium. And we know that in the disk that is problematic, right? Because we have all the spiral arms, we have the bar, we have all these components that don't allow you to assume these stars are in equilibrium. So the sample that we are going to use here is a stellar halo sample. So we only take stars in the halo. but that doesn't mean that you cannot constrain the potential of the disk, right? Because these stars, I mean, for their contribution to the potential, you don't need to assume that they are in equilibrium. It's just when you are using the stars as tracers, okay? So the idea is to use halo stars as tracers, and then you can also include in your potential that you are fitting, you are constraining, you can assume some function for the contribution of the disk stars to the potential, and then constrain that too. That can be done. That's the idea here. Although in this simple case that I was showing here, I didn't include the contribution from the disk, but it's possible to introduce that. So regarding if this can only be applied to the Milky Way or other galaxies, so this inside the Milky Way, this can also be applied to smaller systems. For example, for globular clusters, you can you might be interested in constraining the total mass gravitational potential of a globular cluster, for example. You can also take a sample there, assume some functional form for the potential of the cluster, and constrain the potential. That's also doable. I still have some hope that this method can actually be extended to external galaxies, of course, not to any galaxy, but at least for Andromeda, for example, because we are starting to have a more detailed picture of Andromeda, and even to have spectra for many stars in Andromeda. And so I hope this can be done. And I think I don't have the numbers in mind, but with Rubin Observatory, Rubin telescope, I think we'll be able to measure proper motions in Andromeda. I think so. And in that case, we would also be able to apply this method there.
More questions? So regarding application to other galaxies, if you would go outside beyond Andromeda, and what is the minimum kind of data that you would have to have? Because I think there you're asking for, I mean, you have very detailed velocities and so on, that you can go with DESI, the prime focus spectrograph, etc. until M31. But if you go to other galaxies and have different tracers, what is the minimum number of tracers you would need to do such work?
Oh, okay. Yeah. So I see two questions here. One is the number of tracers. Yeah. One is the number of tracers. I didn't explore here in this paper, I didn't explore samples smaller than 10,000 tracers. That was more or less the number. I mean, just because I know it's kind of a realistic and even a little bit small sample for Milky Way standards. Nowadays, we have samples larger than that. I would need to test how that works, but it's not a method that you can apply to just you know, a handful of stars, let's say 10 stars or 15 stars or whatever. I would guess at least 1,000 stars. And this is just because these entropy estimates, they are noisy. And the main thing to decrease this noise in the estimates is to increase your sample. So if your sample is too small, the entropy estimates are too noisy and you get rubbish. So, and the other question, so that my impression is that you would need something around 1,000 stars at least. And the other thing is if you need 6D coordinates or not. So in this paper again, I only assumed that I have full 6D information for the stars. But this, for example, this DF fitting method that I mentioned before, where you assume an analytical function for the DF and so on, people already show that it's possible to do that even when you don't have 6D information, even when you have only 5D, I think even 4D information. It's possible to do that. Essentially, you can assume some values and marginalize over these unknown coordinates. You treat them as nuisance parameters, something like that. I suspect the same can be done here, but I didn't do that yet.
Any more questions? We have a question there. Can you come here?
Okay, so I couldn't understand everything, of course, because there are some areas that we haven't passed yet and a lot of things, but I could see that there are a lot of approximations and data that we still doesn't know, so we can use exactly that. But just to know about a little bit more about this area, because I saw that there are some formulas from like 1980, some from 2010, some from 2019. I could see that there are some things that are more recent, some that are older. So
Yeah.
I was thinking, how can this area grow if you need that much information for more approximated things?
I yeah, I'm not sure I understood the question, but let me go here to some of these expressions. So this reference, for example, right? I think that you're mentioning like more like older references, let's say. So the thing is these entropy estimates, this is actually I think the first time people proposed these estimates were in the 80s, I think. So these are not new estimates, but I was like the first to use these entropy estimates in the context of galactic dynamics. So that's the work I did from a paper I published in 2017 and then 19. This is a topic I have been exploring. And so this minimal entropy method is just let's say an application of some of these ideas and of these entropy estimates. And by the way, I forgot to mention here, but with this paper, I'm also releasing the code. It's a Python library that allows you to reproduce these calculations and to estimate the entropy of any sample that you have, things like that. It's very easy to use, I would say. But yeah, apart from that, I don't know exactly what to answer. I'm not sure I got your question.
I was asking more like how do you think this area can grow, like these studies can grow if the data is kind of difficult to acquire?
So how do
Oh,
you grow how do you advance the knowledge in terms of data? Well,
yeah. I think I see. Yeah, in terms of data and also in terms of the theoretical modeling, right? So, yeah, in terms of data is, this thing, like when you take spectra that are more precise and proper motions, we will have DR4 from Gaia, I don't know, maybe next year or in a couple of years, I don't remember. All these will help to make better constraints and advance this. But from the theoretical point of view, so this is one entropy estimate that I used, for example, these nearest neighbors, right? So there are some other, because it's true, this thing advanced a lot in the last years. If you look for entropy estimators on Google, you find many more recent papers that propose corrections to this to decrease. For example, I was showing here, you see the bias in these estimates, right? These estimates are biased. Of course, when you are in 3D, this is much less biased, but still biased, right? And there are some proposals on how to suppress this bias, some different techniques, and there is space for improving this thing here. What else? Yeah, I think that's what I can say for now. But I totally agree with you that the development of this, the evolution of this, does not depend only on getting better data, but also on the theoretical side. The modeling itself can be improved. Yeah.
okay, thank you. There's one more question from Thais. Do you want to ask or shall I ask? Okay, I'm gonna ask then. So do you find that using different stellar populations, for instance, K giants versus blue stars in DESI affects the minimum entropy differentially?
Yeah,
Differently?
that's a good question. So, well, first thing, depending on your sample, that can affect the selection functions that you can have, right? Because here I didn't talk about any selection effects. It's very purely theoretical, error-free. Well, not error-free. I consider data with error, but no geometric cuts and selection functions. So depending on your sample, you can have different selections functions, and that can affect the estimates. But assuming you know exactly how to model your selection function for different samples and you use them properly, you shouldn't have differences in these different estimates. Of course, that you are still assuming that these stars have more or less the same spatial distribution and they are equally well in equilibrium and things like that. So if any one of these populations differ in how well they respect these assumptions, you could have different answers too. Yeah.
Okay, are there more questions? I have just a quick one. What is DESI's wavelength range?
Oh, the wavelength range is, let me see, I have these numbers here. Let me.
If you don't know off the top of your
I
head.
don't remember, but I have this very easily. I can send to you. Sorry.
Optical, right? Optical only. Okay. Okay, cool. So let's thank Leandro, and we can go into the topic. And I thank the colleague that asked a question. Well done.
Okay, thank you.
Bye-bye.
Ciao.